Alright, so this is a video on section 5.4. So we previously worked on defining a function, big F of x, in terms of an integral. And we did the example in class. We used a picture. All's well and good. But now what we're going to be doing is thinking more about these integral themselves and making the connection a little better, a little clearer, between the derivative of a function defined like what we have here and the function inside the integral. So the way that we're going to do that is by leveraging this theorem. So we really we're dealing with this to start, looking at values, just exploring this as area under the curve to understand big F. But a very important piece of this theorem is right here, saying that, okay, if you have this definition, then the derivative of big F is just this inside function. And so if you have things algebraically instead of geometrically, like a picture like we had before, you can just work with this function to try to understand everything. So that's what we're going to do here. So the first step in a problem like this is to say, okay, what do I have compared to what the theorem says? Well, I've got an integral from a constant to x. Okay, well, that's constant to x, so that checks out. And then I also have a function f of t in here, and I see my function f of t. Okay, so everything looks good. So then I look down a little bit and I see then that the derivative of this integral defined function is supposed to be equal to the inside function, which in this case is 1 over x cubed plus 1. So what does this look like? It looks like the derivative of this integral is just the inside function. I just took the x and plugged it in. This hopefully should kind of feel right in a sense, in that when we were talking about integrals, or when in Calc 1 you were speaking of antiderivatives, and so we're almost just applying a derivative to an antiderivative. And if you remember, with very many things in math, when you defined a forward and backwards direction and then you combine them, they ended up in a sense canceling out. And that's one way to think about what's happening here. So now we have a slightly different scenario. Instead of 1 to x, we have 1 to x to the fourth. That is not an x, so something is off here. Well, let's do a different function. How about g of x is what we actually want? All right. If that was the scenario, then I would just get to tell you g prime of x is secant x, and life is good. So what we need to think is, well, how is this different? Well, all that's happening is instead of an x, I have taken that out and put in an x to the fourth. So then, if I do what I just said, I really have this now. Okay. Alright, so that's nice. Well, what this does is, if I think about the left-hand side, it's really a composition. And whenever I have function plugged into function, I could use chain rule. So the derivative of this then, well, use the chain rule. It's the derivative of the outside, plug back in, times the derivative of the inside. But from above, I know what g prime of x is. It's just secant x. Okay, so I'm going to plug that in. That's secant, but instead of x, it's x to the fourth times 4x cubed. Ta-da! All right, let's try one more. So hopefully you look at this one and say, okay, I've got that x squared. Gary did it to me again here. But I've thrown you another curveball. And this other curveball is there is no constant. There's just an x and a power of x. So what I need to do is somehow separate these bounds out to get a constant in. And one way you can always do this is break it up. X to 0 plus 0 to x squared. And you have to be a little careful here with this, depending on what values of x you're considering and all that. But the main idea of this is when you're splitting these bounds up, you can think of it as, okay, an integral is area under the curve. So just in general, if I'm going from 0 to 2, well, that's the same thing as going from 0 to 1 and 1 to 2. So there you can see at 1 I can split up the integral. So you could do that a lot of different ways, but since we're thinking about integrals as area under the curve, hopefully it's not too bad to see that all we're doing is, instead of adding up over one larger interval, we're trying to think of it as adding up over two smaller ones. Now that's not always how this works out depending on the numbers you have, but if you believe that, then you should believe that this rule could be true. And it's worthwhile to look into the different cases you might get depending on how you split things. But for now, we're just going to assume that this is a true thing we can do. And then what we have to say is, okay, well, this one over here, we just did this, so we'll practice that. Now over here, oops, wrong way. Over here, it would be really nice if I could just flip these bounds. And we actually do know how to do this. This was one of the rules we had written down on our integral sheets. I can flip the bounds by putting in a negative. Okay. Alright, so I have this set up now. Remember, the derivative of a sum is the sum of the derivatives, so I can take the derivative separately of each of these. Well, looking at this first piece, the derivative of this first piece, that fits the formula. So I know that the derivative of this will just be negative because the negative's on the outside. Square root of 1 plus x cubed. Okay, so then from here to here we're doing the derivative. Okay, here to here we're going to do another derivative. Right, but this is the same scenario. Again, we have chain rule. So chain rule says it's the derivative, but plug back in your x squared and then multiply by the derivative of the inside. And there you go. So those were the three kind of ways you could see this problem. A composition, so instead of x, it's a function of x. You could see an x on the bottom instead of on the top. You could see an x in both top and bottom where we have to separate. But that's all we'll really come across, and they're just applications of things that we've already seen before. All right, see you in class.